Hello grade 8s, this is Mr. Miller and welcome to lesson 9.2 on patterns in a table of values. So first we want to graph the ordered pairs in this table of values. So we've got x and y, and the x is the horizontal component. As you'll notice that the horizontal axis is labeled x and the vertical axis is labeled y. And you'll also notice that I have made sure to put numbers on my axes so that you can tell exactly the size of things. So very important things to do when you're doing graphs. Now let's put these points on the graph. So the first point is 0, 0, so that's at the origin here. Next point is at 1, 5. And the next point is at 2, 10. So notice how we're doing the horizontal component first and then the vertical. So for instance 3, 15, you go to 3 and then up to 15. And next one is 420, so we go 420, and obviously I've chosen my scale to make it easy to plot these points here. 525 is right there. And we don't know exactly what x and y are supposed to stand for, so maybe we should connect these, maybe not. It's hard to say what we should do for sure here, but let's see if we can answer the questions that follow. The next thing it's asking is, what is the difference in value for consecutive x values? And so what we're talking about here is looking at how much x is changing. So going from 0 to 1, obviously that's increasing by 1. Going from 1 to 2, obviously that's increasing by 1 as well. So each time we go to the next consecutive x value, we are increasing the x value by 1. And so that's why it's a plus 1. So plus 1 for each one of these steps here. And so I'm just going to put here plus 1. Now the next question is, what is the difference in value for consecutive y values? So I'll use a different color for this. So I'll use green. So going from 0 to 5, the change in here is we are increasing by 5. And going from 5 to 10, this is another increase by 5. And so on and Scooby-Dooby-Dooby. Yeah, you heard me, I said Scooby-Dooby-Dooby. Alright, so each time we increase the x by 1, the y is increasing by 5. Plus 5. And so now coming up with an expression for y in terms of x, what you can do, and this is a general rule that will always work for linear relationships, so every time you have points that line up on a straight line, you will be able to take that change in y and divide by the change in x. And when you do that, you will find that it's y equals 5 divided by 1 is just 5x. This is how you come up with the relationship. Now sometimes there's a plus something else. Now there isn't anything else here, and that's because in this particular case we've got a y value. So the y value here when x is 0 is also 0. But that's an important thing to look at, because that y value when x is 0 is what you'll have as your plus something else right here. Now since it is plus 0, we don't need to add anything to this equation. So actually a simplified version of that equation would be to just write it as y equals 5x. And so now this is the equation that relates x and y to each other. So you notice that 0 is 5 times 0, 5 is 5 times 1, 10 is 5 times 2, 3 is 5 times, 15 is 5 times 3, and so on. 20 is 5 times 4, 25 is 5 times 5. So, this is a way for you to come up with an equation from the table of values. Just look at the change in y over the change in x, and that gives you a number, which is the number that multiplies x. The plus something else, if there's a plus anything else, it is going to be the y value when x is 0. So now, to determine whether a relationship is linear, you could certainly plot all of these points on a graph and see that they line up the way that these ones did. And you notice that you know, if I'm to do a line through all of these points, they certainly can, right? They all fall in the same straight line. And so if you've got some graph paper and you want to do that, you can certainly check if a relationship is linear. But there's another way to check if a relationship is linear, and that is to check out whether that change in y over change in x is always the same thing. In other words, if it keeps going at the same slope all the way across the grid, then all the points will line up on the same straight line, and so it will be linear. But as soon as you start changing the slope, changing that the change in y over the change in x, if it's something else, then you're going to have points that are not lining up on a straight line. So for instance, when we look at this particular one, if you look at the change in this variable compared to the change in that variable, so this is going up by 4 every time we go up by 1. And oh, now hang on a second here, because now it goes up by 6 while we're going up by 1. So that's not the same thing. Going up by 4 while this is going up by 1. And this is going up by 6 while we go up by 1. So it's kind of funny because there's obviously a pattern there of 4, 6, 4, 6. But this does not make for a linear relationship, because if you look at the change in t 4 over the change in s 1, it's not equal to the other possibility of change in t over change in s, which is 6 over 1. So for that reason, we know that this is not a linear relationship, because the change in t over the change in s is not a constant. And if you look at this graphically, what it looks like, it is this. So if I'm going to make a graph of something, sometimes I'll use this Desmos graphing calculator. It's at desmos.com/calculator, and I can certainly put my points in here just by specifying them in round brackets. So 2, 5 is a point, another point is 3, 9, and another point is 4, 15, and another point is 5, 19, and the last point is 6, 25. So now I'm just going to change this up a little bit, have x just go from -1 up to, we don't need to go any higher than, let's say, 8, and vertically the y-axis can go from, let's say, -5 up to 30, and that should be plenty enough for us to see everything that we need to for this. Now, at first glance, you might look at these points and you say, oh yeah, looks like these points are all in the same straight line. But as soon as you, so I'm just going to bring up this image, and I'm going to copy that image, and as soon as I put that into my notebook and take a closer look at it, okay, Let's just move this over here, and let's get a little bit of a closer look at that relationship between S and T. So right here, this is where we have our S-axis, and right here is where we have our T-axis. Now, if I were to try to connect all of these dots with a nice straight line, I'd have some difficulties in doing that. It's because of the fact that this is not a linear relationship. So connecting this dot and this dot, hey, there's a straight line. Yeah, but if I continue it, it doesn't line up with the rest of them. So, I mean, here we've got a slope of 4, and here we've got a slope of 4, but at other places it just doesn't work out. If I try connecting that dot with this one and then extend it, that one's too steep for the rest. Anyways, long story short, you can see that I can't really draw a straight line and go through all these points. You say, well, if I made the dots big enough, I could. Yeah, that's true, but that's not really what we want. We want to go through the center of these points, and it's just not working out. So this is obviously not a linear relationship. Again, you don't need to graph it. You can actually tell from the table of values, because you can see here that the change in T over the change in S is not the same. So what about this relationship here between H and I? Is that a linear relationship? Well, let's take a look. So you can see that the change in I here is going down by 3. Change in I here is, sorry, this is going up by 3, and this is going up by 3 again. Each time we're going down by 3. So it looks like this is a constant, right? So if you look at 3 over negative 3, that's a slope of -1 the whole time. And so because of the fact that you've got the change in I over the change in H is a constant, we know that this is a linear relationship, or at least appears to be, from the points that we have here. So now I could certainly graph those points to show you as well. Let's take a quick look at that. So if I just clear this off and I put on the points that we're looking at, so it was 7, -6, and we had 4, -3, and the last point was 1, 0. You'll see that all of these points are on the same straight line. We just need to change the grid a little bit so that we can see all of these points. So that will certainly work for the horizontal axis. The vertical axis needs to go a little bit lower, so maybe from -10 up to +10, and then we should see all of our points here. Yep, there they are. So now I can take this image, let's try that again. Let's take this image. Oh, there it is. And we'll just copy that and paste it into the notebook so that we can have a closer look at this. So let's label this as the H-axis and this as the I-axis. And now if I try to do a straight line going from here to there, I will be able to extend that and go through all of the points. So I might want to make the line a little bit less thick just so I can see my points still. Right? But yeah, obviously this is working out. This is a linear relationship. you can see that all of the points are lying on the same straight line. Of course, you didn't actually have to graph that to figure it out. You can just look at the change in I over the change in H and realize that's a constant to be able to tell that it's linear. So the next thing says, for the following table of values, we want to graph the ordered pairs and determine if the relationship is linear. So if you graph it, it's going to look something like this. Let me just zoom in on that so you can see it a little bit more easily. So we've got our points here at 0, 3 is the first point. The next point is at 2, 9. The next point is at 3, 12. And the next point is at 6, 21. So is this a linear relationship? Well, let's take a look. If we connect all of these points together, we'll go in this nice straight line here. And again, if we just make that a little bit thinner, it'll be a little bit easier to tell if we're really going through all those points. And yeah, it seems to go perfectly through the middle of all those points. So this does seem to be a linear relationship. So yes, it's linear. These points are all on the same straight line. So you can certainly tell from the table of values as well. And I can just demonstrate that here. So if we did the change in V, positive 6, over the change in U, which is positive 2, that 6 over 2 is equal to 3. And now if we do the change in V, positive 3, over the change in U, positive 1, that is also equal to positive 3. And if you take a look at the next one, the change in V, which is 9, over the change in U, which is 3, that 9 over 3 is equal to 3. So there's another reason that you could use to justify this, is that the change in V over the change in U is a constant for the entire table of values here. So in addition to the fact that all the points on the graph are on the same straight line, you've got this additional reasoning. So next thing, we've got Mahisha, who has $100 altogether. She's got some $10 bills and some $5 bills. I'd like to copy and fill in the table of values to show at least 5 possible combinations of $10 bills and $5 bills that Mahisha may have. Let's start off with something simple, like let's say that she has no $10 bills. In that case, she has to have all $5 bills. Well, 100 divided by 5 would give you 20, so you need to have 20 of those $5 bills. What if you have one $10 bill? Well, then you've got another $90 divided by 5, that's 18 $5 bills. And with two $10 bills, you'd find 16 $5 bills, and so on. With 3 $10 bills is $30. The other $70 divided by 5 gives you 14 $5 bills. And how far along can we go with this? I guess we could go to the point where, what if you had no $5 bills? How many $10 bills would you have to have? And that would be 10. So I've kind of skipped some in-between values here because we only had room to do 5 possible combinations here. But the next thing we'd like to do is we'd like to draw a graph of this data and show whether this relationship is linear or not. So I'm just going to zoom out enough so that I can see my table and I can also see my graph. And so now I'm going to plot these points here. So the first point is at 0, 20, so that's way up here. Next point is at 118, so that's right there. Next point is at 216, that's right there. Next one is at 314, and you can see the pattern that's going on here, right? And now we skipped way ahead to 10-0. But you know what? We could always continue this pattern. I mean, it looks to me like this is a linear relationship, right? All of these points are on the same straight line, but it doesn't really make sense to connect the dots because you can't really have the in-between values. You can't have a fraction of a dollar bill, so we really shouldn't connect all of the dots, but we can certainly put these other dots on here following that pattern of every time we have another $10 bill, we're going to have 2 less $5 bills. So going down 2 and right 1 and putting all of these other points on would completely finish the graph. So asking if the relationship is linear, you can answer yes. Sorry, I need to spread this out a little bit more. Just a little bit more room to answer this. So yes, the relationship appears to be linear, and it's because all the points on the graph are on the same straight line. Also, if you look at the table of values, the change in the number of $5 bills over the change in the number of $10 bills is a constant. So just to illustrate that point, if you look at this, it's going down by 2 every time this is going up by 1, and again down by 2 every time this is going up by 1. And so it's that -2 over 1, which is a constant, right? -2 each time for all of these steps up by 1. And even if you take a look at the last one, which is going down by 14, here when this is going up by 7, even that -14 over 7 is the same thing. It's -2. The change in the number of $5 bills or the change in the number of $10 bills is a constant, which makes it a linear relationship as well. Last question, is it possible to have 19 $5 bills? And explain. So no, it's not possible because 19 $5 bills would be $95. So since there's only $10 bills, those are the only other types of bills, it would make it impossible to have $100 altogether. So that's the end of this lesson. Thanks for watching and have a great day.